Hey guys, Mr. Betts here. I want to talk to you about a characteristic of functions that we're going to use calculus to explore, and that's increasing and decreasing intervals. These are ideas that we've talked about kind of informally in the past, and we're going to formalize that now. So first, let's start with the definitions. So I'm going to look at the graph and how that applies to the definitions in a minute, but essentially a function is going to be increasing if we pick any two x values on the interval, and if the first x value is to the left of the second x value, then when we plug those into the function, the first x value would be smaller than the second x value. So it would make sense if the function is increasing for a value to the right to also be bigger. And on the other hand, for an increasing interval, a value to the right on the x-axis is going to give us a y value that's going to be smaller. So increasing and decreasing, we can look at any 2 points on the interval, and a point to the right will either be bigger or smaller depending on if the interval is an increasing or decreasing interval. So let's look at an increasing interval here for a graph and look at how this definition is applied. So we're going to pick any 2 numbers on the interval, x1 and x2. So I'll just say x1 and x2. And if the function is an increasing function on that interval, then the value of the function at x1 should be less than the value of the function at x2. So the value at x1 is right here, the value at x2 a little bit bigger right here, and so this inequality here holds. And that's going to be true for any 2 points that I pick along this interval, no matter how close or how far. I did pick 2 points that were kind of close together here vertically, and if I pick 2 points that are really close together here, these two are going to squeeze in a little bit, but any point to the right is higher than any point to the left, and that's what it means for it to be an increasing interval. So the question is, what does this have to do with calculus? Well, on an increasing interval, what's going to happen is we're going to get tangent lines that are going to have positive slopes. So any point that I pick along here, the tangent line is going to be a positive slope. So the tangent line, remember, closely approximates the slopes of secant lines. So if we pick 2 points, the positive slope there is going to guarantee that this inequality is true. And so what's happening here is by using a tangent line to approximate secant lines, really we use secant lines to approximate tangent lines, that positive slope tells us that the function is increasing. So rather than trying to just pick points and plug them into the function and see if the point to the right is bigger than the point to the left and doing that a bunch of times, we can just take derivatives, and anywhere that the derivative is positive, we're going to get an increasing function. So we have this theorem that says if f is a continuous function on the closed interval from a to b and differentiable on the open interval from a to b, and the derivative is positive for all the x values in the interval from a to b, so this is just saying that x is on that interval from a to b, then f is increasing on the closed interval from a to b. All right, so this is kind of interesting. What it says is that if the derivative is increasing on an open interval, then it's increasing on the closed interval. So before I get to the picture over here, I want to show you what that means. And I'm going to kind of give an extreme example here. Let's say the derivative is 0 at the endpoints. So at any point in between these 2 endpoints, the derivative is going to be positive because we have positive slopes of tangent lines. So what that means is this is an increasing function even if we include the endpoints. So even if the derivative is 0 at that endpoint, it's still an increasing function. And if we think about the definition of an increasing function, and we pick 2 points, so let me pick 2 points on my picture here. Let's say I pick the endpoint and a point a little bit to the right. No matter how far to the right I go, this point is going to be a little bit higher because the derivative is positive as we move to the left. So even though the derivative is 0 at that point, it's still positive as we move to the left. So what that means is if the derivative here is positive for all the x values, then we're going to have an increasing function. I do want to point out that the derivative at this point right here does appear to be 0. So we could break this up. Let's say this is A, this is B, and this is C. We could break this up and say, okay, since the derivative is positive between A and B, then it's increasing on the interval from a to b, and that's a closed interval. And then the same thing, if the derivative is positive between b and c, neither of these has to include b, then it's increasing on the interval from b to c also. Well, if we combine those, sorry, that should be a closed interval. If we combine those, then that gives us the entire interval from a to b. So even if the derivative is equal to 0 at points in between, then the interval is still going to be an increasing interval. Okay, so the note down here is saying that if the derivative is equal to 0 at a point or multiple non-consecutive points. So as long as we don't have a section where we have a horizontal line for the function, then we're going to say that the interval is going to be increasing, including x equals c. Now, I've been talking about increasing intervals. If we just flip a couple of things, in particular, if we say that the derivative is negative instead of positive, then we just change from saying increasing to decreasing. So when we're talking about increasing or decreasing, we're going to be looking at the derivative, and if the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. And again, this note is telling us that if the derivative is 0, that would be part of any adjacent increasing or decreasing interval. So if we want to determine increasing and decreasing intervals for a function, notice the first step here says we're going to determine critical numbers for the function. So that was in the last topic, 5.2. We talked about finding critical numbers. Specifically, that's where the derivative equals 0, or where the derivative doesn't exist. So, or where it's not differentiable. That's going to give us critical values. Then what we want to do for finding intervals of decreasing and increasing behavior, we're going to make what's called a sign chart. And you'll see this in the examples that I do later. And basically what we're going to do is we're going to put the critical numbers on a number line, and then we're going to test values on the intervals between those critical numbers. So between the critical numbers, the function is always going to be increasing or it's always going to be decreasing. It cannot switch. So the derivative can only change signs where the derivative is either equal to 0 or the derivative is undefined. Then based on that sign chart, we're going to determine whether the function is increasing or decreasing. And again, I'll go through some examples of this in the example videos.